In this video, we're going to look at the derivation of these three ANOVA formulas. These are the computing formulas. Sometimes students, see the defining formulas, and it's kind of clear where those come from. They're the defining formulas because they define what we do with the ANOVA test. So if you understand the ANOVA test, these are pretty intuitive. We're going to review those real quick. Because I want those to be understood before we take each one of those and derive the computational formulas that students can see and think, well, where did these come from? Why is this this? Why is this this? And why is this this? So real quickly, let's just think about where these formulas came from. And I do have another video where I prove that the total sum of square differences equals the sum of square differences within each set, each treatment group. Okay, I have three treatment groups here in my little illustration. That plus the sum of square differences between treatment groups. And I would recommend seeing that video first if you want maybe a little more clarity on everything that's going on here, and I have included that URL in the description. But just a fast review of what these formulas are. If you look at this first one here, this y, and sometimes you'll see the formulas. There's several different notations, and that's part of the problem. But I've picked this one because it's a fairly mainstream one. You will have, if you do much searching, you'll see that SST, SSW, and SSB are used pretty commonly, but you will see other abbreviations for these, and so don't let that confuse you. But this here, that y is our random variable. Some systems use x, it doesn't matter. But if you do all the i's and all the j's, basically this is going to be every single point in all treatment groups or all sets, whatever you want to describe. And then this is the grand mean. And what this distance is in here, we're going to take those distances and square them. Well, what that distance is you go to every point and then you go to the grand mean. So I've color coded this green. So here's our grand mean. Here's three sets, each with their own local mean, but then we have the grand mean from all points. And basically, this is going to be all of these distances from every single point to the grand mean. Okay, then we have the sum of square differences within. This W stands for within here. This is within, this is between. Okay, well, within groups, we take every single point in that group and we take the distance to its own local mean. And I've color coded that red. So from all points to their own mean, it's going to look like this. And then we have the sum of square differences. And when you think of difference in math, think of a distance. So sum of square differences or sum of square distances, it's the same thing. And I've color coded that yellow. And that's from each group mean to the grand mean. And so that's going to look like this. These are all going to be the same distance within each group. So that's the basic idea of what each of these distances are. And this is a flawed illustration. We can use it for what it's worth for the intuition, but we're going to square the distances. So these are not linear distances. We're taking them and squaring them. We're making more of a Pythagorean relationship here. And then plus, this is also a flawed illustration because of the fact that, okay, so normally green equals red plus yellow, the way I've done it here. So if you look at this particular point, it looks like, well, this is true. Green equals red plus yellow. But if you look at this point, it looks like yellow equals red plus green. And so the proof that I do on the other video shows that even though some points look like they're doing something different, that overall for this entire experiment, that this relationship does hold. That overall the total sum of squares from every point to the grand mean equals, these distances squared and added plus these distances squared and added. So I still haven't done the proof yet. From here, I'm going to show a little illustration. If you want to practice getting to know this particular notation and using the summations, which these can be quite intimidating to students, I'm going to do that coming up. And then after that, I'll get to the actual derivation. How do we get to this from this, and this from this, and this from this? Quick little correction, I referred to what I'm going to do as a proof a little bit ago. I actually meant a derivation. This isn't meant to be a proof, it's just a derivation of the secondary formulas from the primary formulas. But what I wanted to do was include this. I'm still not doing the derivation yet. We're still on the primary, or what are called the defining formulas, and that's SST, SSW, and SSB. And what I wanted to do is make up a little illustration here, and I use the same illustration in my proof of the ANOVA equation. You can use this or not, but since there's so many different kinds of notations, I thought it would be good to make an example set. So here I have 3 treatment groups, and if you feel the need for more clarity, what I would suggest is take these 3 treatment groups here. They're horizontal. In some illustrations they're vertical, and that will change the notation because of the use of I and J. But since they're horizontal, I can use I to designate the groups. Here you can see I. So like that basically what's going on here is you have your random variable and an I and a J. Okay, so my first observation is 1, and I is 1 and J is 1. And then second observation in the first group, I is 1, J is 2. So I defines the group, and J defines which observation in the group. And so what I would recommend is look over each of these things in the kind of a legend thing that I made here, and make sure you understand where each one of these are coming from, and that you understand these double notations here. And when you do these, basically you take the inside one and you go through one total iteration of J up to Ni, which is the size of the sample group. And then and during this time I is 1. It starts out as 1. And then you finish with that, and then now I turns to 2, and you do a whole other iteration of J's, and then I increments to 3, and you do another one. So a lot of this is really just being really familiar with the summation formulas, which can be quite intimidating and confusing if you're not really used to them. So anyway, my suggestion is, take the example set here and use the primary formulas, the defining formulas, and practice actually going through the total summation process. And you'll see here that the total sum of square distances was 88. And when I did all 3 summations here, these 2 did indeed equal the total, and that should always happen. So if you want to use this for practice, just to get used to the notation and getting used to actually using the summations, then fine. If you're already really familiar with this and you just want to move on to the derivations of getting from these formulas to the computational formulas, then that's coming up. You can go straight there. One last comment, though. Keep in mind that, like I said, if I had done these, like the 1, 4, 10, if I had chosen to do those as vertical groups, well, the I's and J's, we never changed those. So the NI would have to change to NJ to make sense, and it would change some things about the notation. So when you're trying to make sense of these formulas, and maybe you've run into different illustrations in MyLab Math or a textbook or whatever, Primavera, whatever it might be, just be aware that you need to be conscious of whether your treatment groups are being presented horizontally or vertically, and don't let the notation confuse you. You'll be able to make sense of it if you are aware of of how the way it's presented can actually change the look of the formula. Okay, now we're actually going to take the first formula, the total sum of square differences, and we're going to start on the derivation of the computational formula. And I put this here just to have something to look at, because it's very helpful for understanding to have something to look at. Otherwise, it's just too abstract. So again, just to be really clear, the way I did this, the groups are horizontal. I is always on the left, so I. They're all ones. So this is group I, and then this is the number of things in. So this is group 1. I should have said this is the number of things in group 1, and then this is the mean of group 1 or group I. Okay, so same with all of these. Now, keep in mind, like I said a minute ago, I is always on the left, J is always on the right. Nobody ever messes with that. We don't change that. If you decided to, do things, so I'm just taking this group here, the horizontal, and pretending that I had done it as a column. Well, J is still on the left. We don't change that. We change our own notation to match. And so if we did that, we would have to say this is now group J, and this is the number of things in group J, and then we would have, the mean of group J. So it can be done either way. You'll see it done with I's or J's, and it all is coming from, did they think in terms of horizontal groups or vertical groups? So let me just get rid of this. Okay, so hopefully at this point you're completely familiar with what's going on here, where this came from and how the summations work. It's very important to be real good at notation, summation notation, to really understand everything. So what I'm going to do now, I have Yij minus the grand mean, and that's squared. So all I'm going to do is just FOIL this. Just think of this as A and this is B. And if you had, A minus B, and you FOIL that, and hopefully you're familiar with foiling, I'm not going to get into that, but if you FOIL it, you'll get A squared minus 2AB plus B squared. If you don't believe that, try it. You'll see. And so that's all we're going to do. Okay, continuing on, I already did it just to save time so you're not sitting there watching me write, but if you look at what's going on here, you will see that this is the same as this. Okay, what's inside here is the same thing as this. So all I did was take my A minus my B and FOIL it into A squared minus 2A times B plus B squared. Okay, so now if you are familiar with summation notation, you know that you can take the summations, and instead of having a summation over a whole bunch of stuff, you can set one of these. Let me just actually maybe illustrate it. If I have something like that, and I have x plus y, and maybe this is an I summation Okay, well, you can actually distribute. You're not multiplying, but you can do a type of distribution. I'm just writing fast and sloppy here. But if you have a summation of a sum, you can take you can take the summation and write it next to each thing, whether plus or minus. It could be plus or minus here. Okay, well, that's what I'm about to do here. Okay, so I went ahead and did that. So you'll notice that there's a notation symbol in front of each of these three terms. As you hopefully know, terms are things separated by plus or minus. So we have, if I can get my pencil working here, we have three terms here, and so we still have three terms here. I just set a notation system in front of each one of them. Okay, this first one here we're done with. That is part of our final formula, our computation formula. But we're going to work on these two and morph them into something that looks different, and then they're actually going to turn into like terms. So basically what I'm going to do is create some new variables that actually it's not me, they're mainstream. You'll see them. I kind of think of math as building with Legos. You know, you make some new Legos for different applications, or the manufacturers do, and you can do more stuff. So we create more Legos, and then we plug the Legos together, or we substitute one Lego for another one that works better. And so that's kind of what we're going to do here. Okay, so here are some new Legos, and we're just going to relate them to our existing system here. And so TI, what does that mean? Well, that's the total in a given row or a set. This is just the number in each set or each treatment group here. So for instance, here I is 1. So if we're in the ith set, the total of that in this case is, I should put a 1 here. Okay, so if I is 1, we're in this row, and the total of that would be 15. The grand total, well, for this particular experiment, if you total all of these up, 1 plus 4 plus 10 plus 2 plus 6 plus 6 plus 10 plus 5 plus 7 plus 9, you get 60. And then n is just the total number of observations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here n is 10. So hopefully you can see how each of these variables works. And then based on that, we're going to start working on these two terms and doing some substitutions. Okay, so I moved the second row up, I deleted the first row, so really my suggestion is be writing all the stuff down as you follow the video so it's all visible in front of you at all times. Because I want to keep this definitely visible, so you know, as I need to, I'll just keep moving these rows up and eliminate what was there before. Okay, so looking at this second term here, let's think about that thing. That's the grand mean. We would get that from taking the total number of all observations and dividing it by the number of observations. And so we could replace this thing here with G over N. Okay, let's think about what this is. Well, that's just G again. This whole thing here is just G, because all we're doing is taking every single one of the observations and totaling them up. So this whole thing turns into -2 times G over N times G. You know, if you want, you can think of G over N. So what we're going to have, I mean G over 1. So what we're going to end up having is G squared over N. Okay, for this thing, we're going to need to do a little bit of fancy manipulation. So what I'm going to do, this is a constant. It has no i's or j's in it. So as we've seen, we could actually have set that in front here. So here's what I'm going to do. I'm going to put a times 1 because we need to have something here. And now I'm going to move this over here. And we're going to have, actually, while I'm at it, since this is just, this squared is just going to be this squared, let's do this. That way that part's going to be done. Okay, so all I did was I took this and I substituted g over n, and since this is squared, then, we know that this is also true. I just square both sides. Well, here we go. That's this right here. And since I had multiplied that by 1, okay, we can think of this as being a 1 here. So this has been moved to the front and substituted for something else that is the same thing. And now we're just looking at this. So before we do that, let's think about just that thing right there. And let's think about what would happen if you have some summation. So I'm just making this up now. Let's just say, okay, say n is 3. Okay, and you have, just a constant. This would be a 2, a 3, whatever. But just something that does not have j's in it so that your summation keeps incrementing. What would you do here? Well, what you do when you have a constant is, okay, when this number is 1, you do one of these. Now this is 2, so we do this again. Now this is 3, we do this again. But now we've reached 3, so we end. We're done. Sorry, it's supposed to be a 1 there. Okay, and so what we actually end up with is this number here times whatever this was. So just to be clear, you have something something like that and some number out here. Let's just make up a number. This is the same as n times 9. That's how this works. It's the same situation we have here. We're incrementing up to this number, and that means this number has to happen this many times. So bottom line is this whole thing, and I'll do it on the next row after this, but basically this whole thing is going to turn into this. So this first summation, we're just leaving it alone, but now this inside part is just going to turn into ni times 1, which means that it's just ni. And so this is what this all is going to, this all here, that's what that's going to turn into on the next row. Okay, so continuing on here, this is just going to be g squared over n. And then this here was what was formerly this, and we just did a substitution. And then this whole thing just turned into this. Okay, so make sure you're really comfortable with where this came from. But since this is a constant, this whole thing just turns into this number times this number. And so this, this is this number times this number, but of course we don't need the 1 there. So now we're going to continue on with this. Well, let's think about what this part is. What this means is take n1, and then we're going to add that to n2, N3, and until all the groups are gone. So that just means we're going to total this up, and we're going to add it to this total and to this totaled. And what is that going to equal? Sorry, I didn't mean we're going to total all these up. We're going to total these up. All right, sorry about that. N1 is 3, N2 is 4, and N3 is 3. So what we're really doing here is 3 plus 4 plus 3. Well, what does that give us? Well, that's this. That's the total number of observations, which we know is n. So this whole thing is just n. It's another one of these. Okay, so this whole thing, I'm maintaining that it is just n. Remember, ni is not n. Ni is the number of observations in one row. N is the total number of observations for the entire experiment. Okay, so I hope I was clear on that. So what we're doing here is we're taking N1 plus N2 plus N3, and that gives us 10, which is N, and so here we're just going to put N. But now this N is going to cancel out one of these N's, and this is now just going to be G squared over N. That's what this whole thing is going to be on the next line. So here's what that looks like, and now you'll notice that these can't get my pencil to work here. Let me just say, okay, these are like terms. This is just one of them minus two of them. So these are both going to turn into negative G squared over N. And here's what that looks like, and this is now the computation formula for SST. And if you try the defining formula by hand and try this by hand, you'll see this is a whole lot easier. Now, keep in mind that you will see different notation. Sometimes this is with some systems, it's as simple as, it might be just as simple as that, because they're doing a totally different system when they do this. Here, they're saying that X is one of the observations and I is just the number of observations, but it's across all of them. It's not rows, and that's what can be confusing about this. But within the context of that, particular system that we're not doing here, this would just mean total everything up. And but that's what this means, except you total it up and square it. Sorry, it would be squared. Okay, so the main thing that you want to do is don't focus so much on the notation as what is actually going on. When you're doing the total sum of squares, the total sum of square differences, then this first part is always just going to mean square then sum all observations. Okay, that just means that this part here is always going to be, in this case it'd be 1 squared plus 4 squared plus 10 squared plus 2 squared plus 6 squared plus 6 squared and so on all the way to the end. Regardless of the notation, that is what this first part is always going to have you doing. So if you already know what it's going to do and you're anticipating that, then making sense of the particular notation used within whatever system they're using, it's not usually going to be too hard to do. And then this thing here is just going to be, you take your grand total and you square it and you divide it by the total number of observations. So that's kind of what I want to do on for SST. Just regardless of the notation, just think of it more maybe in words. For this part here, you're going to take every single observation and square it and then add it. And then you're going to subtract a fraction comprised of total all of these things up, square them, and then divide it by the number of things that there are. So that's the derivation of the computational formula for the total sum of squared distances. Okay, now we're going to do SSB, the total sum of squared differences between groups. And but first I'm going to adjust this formula because this, as a defining formula, is usually expressed in a little different way that's actually easier to do. So I like the way I did that. Okay, remember in the a little bit ago we were looking at something that had an expression that did not have this particular increment going on. Well, we have the same thing here. We have a j summation, but there are no j's in here. So this is a constant with regard to this. And remember what we do in that case? We just take this thing and we say it's going to happen this many times when we get rid of this thing. So that's all we're going to do to adjust this. This is now just going to be this thing. So this isn't actually part of the derivation yet. This and this, you'll see those both presented as the defining formulas. But I just wanted to be clear that, you know, this is where we're going to proceed from right now. Okay, so proceeding from here, now I am actually going into the derivation. And so all I've done so far is I just took this and FOILed. And I'm going to go a little quicker now because we're doing a lot of what we did for the last one, and I need to speed this up. I know I tend to sometimes rattle on and over-explain things because I'm trying to be exceptionally clear. And so, you know, I'm sorry if you get tired of the over-explanations. Maybe some students appreciate it. But anyway, getting this moved along. Well, now what's going to come next is this Ni is just going to get distributed. Okay, so for this next step, you'll notice that the Ni, there's just one in every term. But now I'm going to take this summation and I'm going to distribute it also. So the summation has been distributed. So now all the Ni's are distributed, all the summations are distributed, and so we're going to keep working from here. Notice I put each summation in front of only stuff that's going to increment according to that summation. The 2 and the grand mean are constants, so I put them in front. The grand mean squared is also a constant. So basically I just wanted all stuff with I in it to be on the right side in the proper position to do summations. And then here are some more Legos, 4 of them. So we're going to look at this one, this one, this one, and this one, and make sure that we're totally clear on how that all works, because these are what are going to make this derivation. Okay, before proceeding, so I just moved this up a row to clear up some space, and now we're going to look at these 4, you know, I'm calling them Legos. My little analogy here, but let's just think, what is this first one? So the mean of a given set, so it would be one of these things. That's equal to Ti over Ni. So let's just make an example here down below. So say we have Y1, the mean of row 1. Does that really equal Ti over Ni? Well, Ti is the total of the row. Well, if I total up this row, I'm going to get 15. And then if I divide it by the number of things in the row, that's going to be 3, and that's 5, and that's exactly what this is. So regardless of what we're doing, that's going to happen. So hopefully, that makes sense to you. And then we've already seen this, so I'm not going to talk about that right now. Let's move on to this one. So now if I'm totaling up all the ni's times the, y mean i's. So if I was 1, we would be doing 3 times the mean, and then we would be totaling that with, okay, now if I is 2, well, we're going to have 4 times 6. And then if I is 3, we're in this group, and we're going to do 3 times 7. And so we're going to get 15 plus 24 plus 21. And we're going to get 60. Well, that's just G. So when you see this expression here, we're really just totaling all of the observations. Think of it like this also. If you total up these, that's 15. Well, that's the same as 3 times the mean. Same thing here. If you total up these, you're going to get the same thing as 4 times 6. That's how averages work. Each observation added up is going to be the equivalent of 4 times the average, because, another way we could think of this is, okay, what if these were all 6s? We're saying the average is 6 anyway, so it's going to be the equivalent thing. So 4 times 6 is going to be the same as totaling those all up. The last one here. We saw this one too. That's just going to be, so N1, it'd be N1 plus N2 plus N3. We're just totaling up those. That's just going to give us N, general N, the total number of observations. So, make sure you're real clear on what's going on here so that it makes sense as we continue on with our derivation. Okay, so looking at this here, I've already copied part of it down, but this part here, we're going to do a substitution, because if this is true, then we know that this is also true, and we can take this thing and just substitute . Okay, so we'll leave it like that for now, and moving on. We already know this thing is just G over N. And then we've already seen that this thing is just another G. So there we go. And then again, same thing here. We can just square all those, and we can replace that with G squared over N squared. And then this thing here is just this thing, and that's just another N. And then actually this thing here, instead of putting the parentheses on there, I should have just put a square on the top and the bottom. But now, this is going to cancel out one of these. So let's just get rid of that. And so here we have Ti squared over Ni. So these are going to be gone in the next one, the next line. And then what else? Okay, over here, so this end's going to cancel out one of these. So let's get rid of this square. Okay, so I just shifted that up, and now continuing on here. So we're going to have ti squared over ni minus 2 g squared over n plus g squared over n. And now, same thing as last time, those are just going to combine. And so this is going to be one of these minus 2 of these. That's going to give us negative 1 of those things. And there we go. That is our derivation. Let me clean up that I a little bit. So this is the computational formula for SSB. And again, just like the last one, if you try doing it this way and try doing it with the defining formula, well, the defining formula is just way more busy work. It's way more of a pain in the neck. And I'll emphasize, just like I did with the last one, it might be helpful to take this and write it out in words, because even though the notation will change, what's actually going on will not. So sometimes it can be really helpful to express in words what's going on. That way the notation's not going to, if it's different than this, it's not going to confuse you. Okay, so we've derived the computational formula for SST and SSB. We haven't done this one yet, but it's real easy because we know that, SST equals SSW plus SSB. So really all I need to do is just take SST and subtract SSB, and we're going to get SSW. So that's all I've done here. So I just took this, wrote it here, took this, subtracted it here, distributed, so you can think of that as a negative 1 if you want. We distribute that negative over the parenthesis, and then this is what you get. But then, g squared over n minus g squared over n, those cancel out, so those are gone, and the only thing that you have left is what we've got right here. And that's SSW. So normally you don't need all three formulas. When you're doing an ANOVA test, if you take two of them and, like if you took SST and you had SSW, well, to get SSB, just subtract those. And you wouldn't bother using, the formulas for all three of them. You'd use it for two of them, and for the third one, you would just subtract. So those are the computational formulas derived from the defining formulas for the ANOVA entities SST, SSW, and SSB.